Hello, today I want to talk about a method for solving static force balance problems. The method relies on 7 steps. The first step is get a good free body diagram. Next, you get a unit vector for each force or couple. You get a position vector to each force. You establish the moment of the unit vector of each force. You write your static force balance such that the resultant force and the resultant moment about a reference point vanish. You strategically do dot products or arrange into a matrix equation, and then you solve for your unknowns. Let's look at an example today of a moving platform that moves around in the plane, and the moving platform is supported by 3 legs. Each leg is an extensible hydraulic cylinder that can extend and retract. The ends of each cylinder is a pin or a revolute designated by R, and the leg can extend, and that's designated by P or prismatic. So each leg is a revolute, prismatic revolute chain, and the 3 legs work together to move this platform in some desired way. Let's imagine for a moment that it is fixed in this position and we lock down the 3 prismatic cylinders, and then we load the platform in a way like this. Okay, so imagine that we know the coordinates, the XY coordinates of all 7 points, the origin, and then the other points of the cylinders, and then the application load or the applied load is on the top of the moving platform. So let's see if we can generate a free body diagram for this of the moving platform. So to do that, what I want to do is I want to identify the lines of action of each of the legs, which I've done. I've got scalar forces and unit vectors for each leg. I call it the A leg, the B leg, and the C leg. I've identified the orientations of each of the legs, the A leg, the B leg, and the C leg. I can get that information from the knowledge of these coordinates. So I feel like I should be able to get the unit vectors. I should be able to get a position vector to each of those 3 forces. The 4th force is the applied load, the FL load, and I've got FL and a UL identified for that, and I've got a point, and I'm going to say for the example today that this is pointing in the negative Y direction. And I also know that it's 1,000 newtons for this known load. So what we're going to be trying to solve for here would be the 3 leg forces, the FA, the FB, and the FC scalar loads here. And I believe that this is a good free body diagram of the moving platform. I've got 4 loads identified, located. I've got 1 known value, and I've got 3 unknown values. So I believe this is a really good free body diagram. I have enough information here to declare what the unit vectors are for the forces, what the position vectors are for the forces, and I should be able to identify a static force balance equation from the free body. So I restated those 7 steps for this one, and we've done the free body. So we're in pretty good shape so far. Let's see if we can get the unit vectors for the 4 forces. So I've written here in great detail the unit vector for the A leg. And what I did is I set up to solve for the distance between points 1 and 4. So since I've done a minus x4 and minus y4, I've used the fixed pivot of the A leg as the reference. And I've done that for my distance equation. And I've done that for my cosine equation, which is going to give me the adjacent for the triangle. It's going to give me my adjacent, the cosine for alpha A. the delta x over dA. And then the sign is going to be opposite, or the delta y, using y4 and x4 as reference. And then I'm able to calculate, I'm able to put in my numbers for x1 and x4, y1 and y4. I'm able to put in my numbers to calculate what the cosine of alpha A is and what the sine of alpha A is. And then I can use the equation I've been talking about for a while now, the poor man's arctan 2 or 4-quadrant arctan function. So you do the inverse cosine of the cosine and you multiply it by the SIGN of the SINE. So that's good. It's obviously plus 1. The sine of the sine is plus 1. And the arc cosine of this is 44 degrees, a little bit more. That looks about right. So with this CA and SA, I've established what my unit vector of the A leg is. And then for the B leg, what I want to do is look at x2, y2 relative to x5, y5. And it just turns out in this example, the x2 and the x5 are identical. So that means that I have no delta x, and that means that the cosine is going to be 0. Of course, I easily calculate my distance between points 2 and point 5. Easily calculate that, and when I do my sine, the delta y over my distance, I'm going to get a plus 1. So that means that my alpha b is going to be plus 90, and that looks about right. So I've established my CB and my SB. So this is, again, a special case for my platform here. Let's look at the C leg. So here we will use 6 as the reference, x6, y6, and we will be looking at what point 3, x3, y3 is doing relative to that. This one's getting out of the first quadrant now, and we're looking at a negative delta x because 3 minus x3 minus x6 is going to be a negative value, and I divide by the distance between. So I'm looking at the x3, y3 and the x6, y6. I'm looking at the distance between those points. And then I'm looking at how the delta x is situated. It's a negative. The delta y is still positive. Obviously, this is a second quadrant angle. And the SIGN of the SINE is going to be plus 1. But when I do arc cosine, it's going to give me the correct 124 answer here. So I'm in pretty good shape. I've got my UA, my UB, and my UC squared away for my unit vectors for those 3 legs. And then the last leg, or the last force, I'm sorry, is going to be the given or the applied load. And that's, we're going to take that as going negative 90, which is going to give me a negative J for my UL. And you want to observe when you get this in a web gem or something, you want to observe what your UL is and make sure that you understand the actual direction there, because it may be different than a minus 90. All right, so we've got our free body, we've got our unit vectors and the direction of the forces. So next we're going to go get position vectors and then moments of the unit vectors. So here I've redrawn the free body. My position vectors for the A leg is going through the origin. So I'm good to go there. And I'm just going to use the fixed pivots for the B and C leg. So that's pretty straightforward. And then my load, I'm going to use x7, y7. That's what's given. So pretty good there. And then I just repeated what my unit vectors are so that I could go and take moments. And this is a little bit laborious. I know I'm going to have 0 moment because my RA is 0. Then I go to my B. I'm going to go the RB crossed into my UB. And I can put that, could have done that straight away, put that into a 2x2, because I've got position and a unit vector both in the xy plane, so I know I'm going to only have a k component for my moment, and it's going to be simply that. Then I put in my unit vectors here so I could go calculate what the heck these things are. So I put in my x5, y5, and I put in my CB, SB, and I can figure out what my RB is. Actually put a number on my RB, which is going to be the signed magnitude that goes with the moment of unit vector. Repeat for the C. So for C, I'm going to use x6, y6 crossed into the unit vector of the C. I put in my values, x6, y6 there, and I put in my CC and SC. I get my value for RC, so I'm good there. And then the last one is my RL cross UL. So I've got my x7, y7 crossed into CL, SL. And then for the simple example, I've got the -1 for SL. And I'm going to end up with the minus 3.98 meters. Now that's minus x7. So this little bit of a simplification here, but RL is equal to minus x7 on this example. And then on my RA, I've just went ahead and labeled that as 0. Okay, so we've got our position vectors, we've got our moments. Now we're ready to go do establish our force balance equations, force and moment. So the way I write them is I stack my resultant force as a vector above my resultant moment about the origin in this case. So this is like a 6x1 in general when we go to 3 dimensions. So I've got my force scalar times my unit vector, force times unit vector, force times unit vector, force times unit vector. So that's a force, that's a force, that's a force, that's a force. Sum those up, that resultant should be 0. And then I've got the moment, so I've got the moment, this is about the origin. I've got the moment of the force, plus a moment of the force, plus a moment of the force, plus a moment of the force. So the resultant of all those moments should be 0 or vanish. So that's straightforward. What I do is I think about, since you've got the force, that's a scalar. The FC, FB, FL, FA, those are all scalars. So I could pull those out. And I like to do this because it helps me see if there's an unknown force. It helps me sort of navigate it. So I pull that scalar force out, and then I still have my vector over vector here. I've got my UA and then my moment of unit vectors. So this is what we've already calculated. So we're kind of ready to go, or maybe even symbolically now, we're ready to kind of plug in what my UA is, what my UB, UC, UL, and then my moments. Since we're dealing in the plane today, there's going to be they're all going to have that K, and I've been using the capital R to designate the assigned magnitude of those values, as we know. So this is what I like for you guys to show. Start with this. Show me that you understand that, and you know that these 4 loads are what's applied to the body, plus, 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 plus. Then you make your symbolic substitutions. This really helps so that you don't have any SIGN errors. Okay, so we're finished with the first 5. Now we're going to figure out how to get a strategic dot and kind of get it in. We want to get towards this form here, something of that nature, so we can solve for unknown leg forces. All right, so we go back to that symbolic equation we had last. Okay, and then we can think about doing the resultant, which is going to be the first vector, top vector. Do a resultant dot with I. So when we do that, we're going to get this equation. When you do a dot product with a vector equation, you're going to end up with a scalar equation, and I dot I is 1. So and I dot j is 0. So what's going to happen is you're only going to pluck out the cosine pieces of the force terms. So that's what you're going to get there. And then you're going to do this. You're going to repeat this, the resultant vector dotted with j, and for the same reason, j dot j is 1. You're going to be, and I dot j is 0. You're going to be plucking out the sign, and you're going to be getting an equation in terms of the signs times the various scalar forces. And then the last one is where you're going to take the resultant moment and you're going to dot it with k, and that's all you have. So you're going to end up just plucking out the r's here, because k dot k is 1. You're going to pluck out the r's out of the bottom equation. So you end up with these three scalar equations. And then you want to think about going to a matrix form here. Okay, so this kind of jumps out at me. I think about, hey, my unknowns are the three leg forces, FA, FB, FC, right? So I kind of get them squared away there in my mind. Then the next thing I do is I kind of build a 3 by 3. So I'm looking at these three equations right here, and I'm focusing on these parts of the three equations, and I see FA, FA, FA. So that FA is going to multiply this column, and it's going to give me CA times FA, SA times FA, RA times FA. So that's why this is the first column. And then the second column is going to multiply FB. So I'm going to see FB, FB, FB. It's going to multiply these. So that's why these three numbers form the second column. And then the third column, FC, I look at this, I see FC and multiplying that. So that right there, these three numbers form the third column. So that's how they form the columns. And then what's left over is sort of baggage, and I just leave the FL kind of factored out, and then I have the CL, SL, and RL kind of right there, equals 0. So I've got a good matrix form. It's valid. I like to go ahead and show it like this in my mind so I don't mess up SIGNs here. Okay, but the first row of this matrix equation is that equation. The second row of this equation is that. And the third row is that. So it's almost like you could go straight from this right to that. So we get this, and then after I get this, I then transition to this. I take this and put it on the other side, and I negate it. For our example, SL is -1, so you end up with minus minus equals a plus. And then here, RL equals minus x7, so you have a minus minus equals x7. So this is what effectively we were looking for in that last step, because again, this is because of the alpha L of this problem. Yours may look more like this in general. So we kind of have everything here. I've just written it out as cosine sine, but I think everything that we had on that previous slide is right there. So we've got that form, and we're kind of ready to solve for our unknown leg forces, the FA, FB, FC. Let's see if we can do it. All right, so restated my unit vectors. I got my moments of unit vectors here from our previous. This is the equation that we were striving for. So I go ahead and put my numbers in, my CA, my SA, there. Got RA is 0, CB, SB, 0, 1, and then my RB is 3.65. So I try to put in units when they need to be. So this bottom row, those are moments of unit vectors, so they would have units of length. So I try to put those in. And then RC, we have that, so I put that in. My FL is 1,000 newtons, so I've got that in. I've got 0, 1, and 3.98 meters for X7. So that's the equation that I want to solve for my three unknowns. So I restated it there. What I need is I need the inverse of this matrix, and I've generated that, and I tried to again be careful with the units. because I actually have meters to the -1 there in that third column. Then when I take this matrix inverse and multiply it into the right-hand side vector, I get the solution vector. And FA is 416.2 newtons, FB is 270.2 newtons, and FC is 531.2 newtons. And if you look at the geometric layout of this, you see that the load, the line of action of the load, very nearly passes through the line of action of the A leg and the C leg. Had that line of action of the load passed perfectly through there, that would have meant that the B would have been 0. But as you see, it's a little bit off of there, and the B is not 0, but it is very much smaller than the A leg and the C leg. So the A leg and the C leg are dominating because the line of action of the applied load is closer to that point. The other thing, a couple of things here I want to point out while I'm looking at this. You see that the lines of action of the 3 legs do make a triangle. That triangle needs to have a non-zero area. If it had a 0 area, that means that the B would have also passed through that line of intersection. And that would have meant that you couldn't solve for the 3 loads. Okay, so you need to have that triangle there. It is very cool and related that the matrix is invertible if and only if the area of this triangle is non-zero. So we've finished all 7 steps of our strategy or of our process for this example. Let's kind of recap it. First thing we did is we did a free body diagram. The second thing we did is we got our unit vectors for our forces. And I even numerically, after I numerically determined them, I labeled them as CA, SA, CB, SB, and so forth. Third thing was we got our position vectors to our line of action of our forces. The fourth thing is we got the moment of the unit vectors and label them as RA, RB, RC, RL for the signed magnitudes. We put together our static force balance equations. We did first a statement like this in general, then we made our symbolic substitutions. We gathered our equations in such a way that we had a matrix equation that we could easily solve. And then we solved it. So in summary, we've established some principles for a process that we can attack and solve any static force balance problem we get. Hope you've enjoyed today's discussion.